So for the example of beta tan x minus x plus beta tan h of x, I will just write it down here. So the example we are considering is x dot equal to minus x plus beta tan h of x. Now we divided this into two different equations, that was y equal to x and y equal to beta tan h of x. Yeah, you can take minus x also, it will also give you the same results, no change. So now when beta was less than 1, we had y equal to x graph like this, and we had this beta tan h of x being going like this. So you have only one fixed point here. Now you need to know the stability of the fixed point. So for that, if you observe, beta tan h of x is greater than y equal to x here in this region. So that means the entire total value will be positive. So it will go in the right direction. Now in this right side region, if you observe, y equal to x is greater than the y equal to beta tan h of x. So that means your entire value is negative. So it will go in the left direction. So that means this point is a stable fixed point. Now when you are going for a next step where beta equal to 1 we were having, so you had y equal to x passing through this, and you had the diagram like it was more tangent to your line and it went like this. Now here if you observe the fixed point thing, here you can observe that in this region y equal to x was greater than y equal to beta tan h of x. So that means it is negative, and that means it should go in the left direction. At the same time, here y equal to x is greater than y equal to beta tan h of x. So that means it should be positive. So it should go in the right direction. So that means now it has become unstable. So this point has become now unstable. Sorry, y beta tan h of x is greater than. Okay, sorry. So here y equal to beta tan h of x is less than y equal to x. So the entire equation will be negative. So that means it should be in the leftward direction. And at the same time, here if you observe, y equal to x, sorry, beta tan h of x is greater. Since you can see this is the curve, okay, I should have drawn it with red. So this is beta tan h of x, and this is y equal to x. So y equal to beta tan h of x is greater than y equal to x. So that means it's positive. So it should be right. So eventually it's a stable fixed point. So now the final case where you have beta greater than 1, you observe that y equal to x line is there, okay, it's passing through 0, and you had a curve like this. Now if you observe, you have 3 fixed points over here. In this region, tan beta h is greater than that, so it's positive, so it should go like this. And in this region, y equal to x is greater than that, so it should be negative. At the same time, in this region, beta tan h of x is greater than x, so it's positive and it should go there. And in this region, y of x is greater than, so it's negative and it should go in the left. So that means you have 2 stable fixed points and you have 1 unstable fixed point. So now here also, if you look at the bifurcation diagram, Here the bifurcation parameter is beta, because beta is what we are changing here. And if you plot against x, you will see that for beta equal to 1, up to 1 you had a stable fixed point, then above this you had two different stable fixed points here as shown here, and this 0 became unstable. So this is a powerful tool to understand the dynamics of practical systems which have any symmetric. So after this particular point, system can either show this state or this state. So these kind of practical systems are more seen in real world systems. So this is about the supercritical pitchfork. Why it is supercritical and subcritical, I will just mention once after I mention the subcritical region also. So now in a subcritical pitchfork bifurcation, what is the difference? So the difference is in this term x cube thing. So till now x cube was acting as a stabilizing thing, and it was helping you to stabilize the system to two stable fixed points. It was able to help. Now when you are having Rx plus x cube, now x cube acts as a destabilizing system, and it eventually takes your system to unwanted or high infinity states. So we will see how that will be, that we can graphically see in the system. Just share the screen. So in a practical system like this, we are having, yeah. So now in the system when you have Rx plus x cube, so if your value of parameter is less than 0, you will see that your system had three fixed points, 1, 2 and 3 fixed points it has. And now when as your R is changing, and at R equals 0 you have one fixed point, and further if you increase R, you will see that your system has only this fixed point. And if you observe the stability, you can directly say that this side is all negative, it's less than 0, so it should be going in the leftward. This all is in positive, so it should be in right side. So this means it's completely unstable. Now the system has moved from three points, it eventually came to 1 point, and it finally went to very high amplitude or unstable state. Now we will see how this is different from a normal supercritical pitchfork bifurcation. Yeah, so now in a real physical system, as we saw, so subcritical pitchfork bifurcation, the normal form of this is x dot is equal to Rx plus x cube. Now how the system behaved in this case, we will just go through that. So the equation was x dot is equal to Rx plus x cube. Now when you observe the values here, when R was less than 0, you observed that the system had two fixed points, here, here and here, three fixed points it had. Now if you draw the stability of this, you will see that this is positive, negative, positive, and this is negative. So that means this is stable, this is also stable. Sorry. So the actual diagram was like this. Now you have three fixed points over here, and when you are this x dot when you are plotting, you will see that this is negative, so it should go in the left. It's positive, so it should go in the right. This region is negative, so it should go in the left, and here it should be positive. So now if you observe, this is unstable, this is stable fixed point, and this is an unstable fixed point. So when r was less than 0, you were seeing that, and when r is equal to 0, you observed that the system had only one fixed point, and this was like it had this. Now system is in this, it's negative, so it should be in the bus, and this is the fixed point which we have. So at r equal to 0 itself, if you observe, the system has started being the fixed point is now unstable. Now when you further increase r to higher values of greater than 0, you observe that system has transverse like this. This is the fixed point, and this is negative, and this is negative. Sorry, this is positive. So that means this is also an unstable fixed point. So once r equal to 0 it started, it completely became unstable. So if you plot the bifurcation diagram for this subcritical pitchfork bifurcation, you have r over here and you have x over here being shown. Now when your r was less than 0, you had fixed point as r equal to x is equal to 0 was a fixed point over here as shown here, and remaining two were unstable. So they are represented by the dotted lines here. So this is a stable, this is unstable, this is also unstable. Now after r equal to 0, you will observe that there is no stability, it is all completely unstable. So it's completely went from stable to it became unstable. So there are no further fixed points for the system, it is completely unstable throughout for r greater than 0 case. So now for a pitch supercritical, you had a smooth transition from here, and just show it like this. So it was stable here and it went like this, whereas in a subcritical you have only the stable state before the critical point r equal to 0, and after that you are completely unstable. So that's why, so the name suggested as subcritical suggests that before the critical value your system is stable, whereas in supercritical you have two fixed points that are emerged after the critical point also. So that's the why the name subcritical and supercritical pitchfork bifurcations is being given to the system. And supercritical bifurcations are also sometimes referred to as forward bifurcations, and or they are also called continuous bifurcations, and sometimes also referred to as second order phase transitions. So second order phase transitions in the sense these kind of smooth transitions from one state to another happens in statistical physics. They refer to these kind of growth or some phase transitions, they say, that is from one state to another. When the system changes, if it moves in this smooth transition, they call it as second order phase transitions. At the same time, for a subcritical bifurcation, they also referred it as inverted backward bifurcation. That is, before r equal to 0, you have all the stability and all being referred, and it is a discontinuous, because after the point r equal to 0, the system is completely unstable and you don't have any other growth or any small change is not there, it's completely abrupt. So these kind of things are also called discontinuous or first order phase transitions we refer. So first order phase transition in the sense there is a sudden jump from one state to the other, that we can clearly observe from the bifurcation diagram. When r was less than, for a supercritical case, at r equal to 0, you still have a stable fixed point and it slowly grows out to two different branches, whereas for subcritical, at only stable state is less than 0, and at the point 0 onwards you are completely unstable, so you are being completely thrown out of the stabilities in that case. So in that perspective, if you look, supercritical bifurcations are soft and safe. So they are safe in normal operations. If you observe supercritical bifurcation, people are not very much afraid of it. But if you are having a subcritical bifurcations where you are having their sudden change from one state to another, if you are observing, so they can lead to very catastrophic effects, and these kind of oscillations are observed in various systems where I will explain in the application level what are these systems which shows these kind of things. So subcritical bifurcations are more dangerous, and so you need to be, so they, in these cases you will be trying to do this kind of prevention. Controlling is different, but prevention, you try to do the prevention rather than getting the oscillations in this kind of, in any system which shows this kind of subcritical bifurcation, it's dangerous. So that's the part. And before that we need to tell, okay, so one more thing to be remembered is, so here you have some equation like x dot is equal to rx plus x cube, and this means in the graph it showed that it continuously goes to infinity, but in actual scenario you will not see such things. You will not see an oscillation that is growing infinitely to very high things. There will be lot of damping things that will be coming into action when you are reaching to certain kind. So in order to model that into the equation, the normal form can be written for such equations as x dot rx plus x cube minus x to the power 5. Now when you put minus rx to the power 5, we keep in mind that this should be still an invariant set. Invariant equation it should be, that is, if you put x equal to minus a, system should be symmetric, it should show the same equation once again, and these two things are still maintained when you are putting minus x to the power 5. And yeah, so that's one thing, and that's it. In order to replicate the actual practical system dynamics, we usually use that minus x to the power 5 things. And in the book you may have seen different bifurcation diagrams, first branch and second branch you might have seen. So I will just brief that what it is actually. So in your equation, that is x dot is equal to rx plus x cube minus x to the power 5 equation, if you see, when you are drawing the bifurcation diagram for this, at r equal to 0, that was your normal subcritical half bifurcation. So this was your normal subcritical half bifurcation. You have stable here, you have unstable points here, and when your r value is x to the power 5, so now minus x to the power I acts as a stabilizing effect. Now after that, after this point, you will see that there is a stabilizing effect, and your system eventually reaches to another stable branch. Now how, so this means that at a particular point, at this point, say you have 5 different solutions to the equation, and that should be there because you have fifth order, so you will have 5 different solutions to it. So I will just show you in the Desmos how this solution can be visualized. So are you able to understand, or is there any confusion? Okay, so this was the equation, and when your term which was less than, if you consider it is less than 1, say if it is, this is your critical parameter, and okay, so if it is greater than 0, you will have 2 fixed points here, 1 and 1 here, and this is now it's negative and this is positive, so it becomes unstable, and these two become stable here. And when your value was less than 0, you will observe that you have only one fixed point, that is this is positive and this is negative, so it's a stable fixed point here, that is at 0 you will have a stable line. That was the dark color which we represented. But when r equal to r critical value, say this is the critical point. So now if I zoom it here, you will observe that you have 1 2 3 4 5. So you have 5 fixed points for this system at this point, when it is less than, when r value was at minus 0.2. Now if you draw the stability for each of them, you will get the graph of that stable upper branch. You will get in between these points will be unstable. So if you see this stability of this point, this is less than 0, so it will be in the left, the arrow should be towards left, and this is in the positive value, so its arrow should be towards right. So this is an unstable fixed point. Similarly, this is also an unstable fixed point, but this point is a stable fixed point, where you have this goes, arrow goes towards the right, here arrow goes towards left. So this is a stable fixed point, and this is also a stable fixed point. So this is how the graph which we drew came out. So this is the graph which I just showed you. So when r was 0, you had only one fixed point like this, and when r was at minus 0.2, you had two graphs that were going like this, and you had 5 fixed points for it. So if you take a line, these are the 5 fixed points for that. 1 2 3 4 5. So these were the 5 fixed points, and so in a bifurcation diagram, at a given parameter value is what you are plotting. So that's why these 5 are there, and these 2 are the unstable points, these 2 are the fixed points, stable fixed points, and these are the 2 unstable fixed points, and the 0 was stable at that point, so that's why you will get a stable line here. So this is how in a real practical things you will see, try to replicate these kind of dynamics of the system using pitchfork equations, and adding a additional term can give you more realistic solutions which are seen in the real systems. Yeah, so did you understand, or are there any questions in this? Yes. Okay. Yeah, so next, so now I will just go to an example where, so the example which we will now see is called, so it's called an overdamped bead on a rotating hoop. So we will, so first I will show you how this actual problem is, then we will try to solve them without touching the analytical equations. So for that I will show you a video. Yeah, so the rotating bead problem in this thing is, so now you have a ring or a hoop that is being shown here, and you are connecting that to, connected it to a string that is shown here. You can see my cursor. Yeah, okay. So this is the joint holding point for this hoop, and now, and this hoop at this point, the hoop, the circular hoop is being rotated. I'll show you the video. So about this vertical direction we will be rotating it. So now when you are rotating that, this, so this violet marble, it moves up and down, as you can see here. Yeah, so this is the actual thing. So when you are driving this thing at a certain frequency, what happens to the system? Does it have a single stable state, or it sits at the bottom state every time, or does it has any other fixed state where it is stable when your frequency of oscillations, or this again among about this vertical axis which I have shown here, if they are rotating at very faster rates, will the bead be able to remain here at the fixed state? Is there anything, is what the main question is. So are you able to get the question, what we are trying to do in a overdamped bead? So you have a angular frequency that is given omega, and you have a bead sitting over in the thing which is less frictionless. Now when you are rotating it at certain frequencies, is the bead stable at any particular position, or it is stable every time at the bottom, is it or not, is what the main question we are trying to address. And we will see, can our theory or whatever we have learned till now, can it be useful in telling how the system will behave. So were you able to understand the question, which what we are trying to do in this? Okay, so yeah, so I have drawn the diagram here. So you had a circular disc or hoop here, and you had a marble or ball being sitting over here, and you had a vertical thing that is being growing at a frequency of omega. Now we just try to solve the thing and see how can you draw the bifurcation diagrams, and is there any states stable for it or not. We will just see through it. So in this case, so in the marble position, when it is here, say you have from the vertical distance, you have some rho is the parameter which shows the distance from this vertical, and you can write this rho is nothing but, from the trigonometry, this is nothing but r sin phi. If r is the radius of this hoop, then rho is nothing but r sin phi. From the trigonometry you can know that. Now we want to know where the hoop can remain stable, or that's what we are trying to, stable fixed point. Is there anything like that for this system? Now consider the marble which they have given, and if you try to sort out the forces that are acting on the ball, you can see that there is a gravity effect, that is the weight mg is acting downward. At the same time, you can resolve it into two components. We are writing here only the sine component here, that is acting in this direction, mg sin phi. So that is the second force that is acting. And apart from that, since the bead is rotating, since it is rotating in this omega direction, you in the video you have seen this has some centrifugal force that is acting on it, since it is moving in this direction. So there is a centrifugal force that is nothing but mr omega square. R here in the centrifugal force represents the distance from the point of rotation. So it's like the vertical position which we had and to the point where the bead was sitting. So it is nothing but rho. That's why we wrote it as m rho omega square. And now the component that acts along this opposite to the mg sin phi is m rho omega square into cos phi. So it's nothing but this component cos phi, and you have a vertical component sin phi. So r and m rho omega square sin phi gets cancelled, so we are not concerned about that. So we are only taking the forces that are acting on the system, and apart from this you have a damping term that reduce, or if you have a friction in the system, that is quantified by this b phi dot variable. So this b phi dot is nothing but, if you remember, we had a spring mass system. So this spring had some resistance, and it was proportional to the velocity of the thing. So F is equal to kx we used to write. Similar to that, for the damping term, we have the velocity, that is phi dot is reduced. So b is a factor that you need to consider. So that's why the factor b phi dot is used for represent the damping of the system. So now these are the forces acting on the system, and if you try to equate to, say you have a Newton's simple equation called F is equal to ma. Since our barbell is moving in a circular direction, you will have a tangential acceleration instead of normal acceleration. So tangential acceleration is nothing but r phi double dot. It's nothing but r omega square d omega by dt. You can take it as phi double dot. Okay, that's simple representation things. So finally, the force that is acting on the system is nothing but, so we consider the notation as towards down is considered as negative, and when it goes towards upside it's considered as positive. So in that sense, you have minus b phi dot in the negative direction, then you have minus mg sine phi acting in the negative direction. At the same time, you have a positive term m rho omega square cos phi in the positive side. Now this force is nothing but ma. So m into acceleration is nothing but r phi double dot. So this implies minus b phi dot minus mg sine phi plus m into, so rho I will write it in terms of from the equation 1. So from equation 1 I can write rho as nothing but r sine phi into omega square cos phi. So this is equal to the mr phi double dot. So finally you will end up with mr phi double dot is nothing but minus b phi dot minus mg sine phi plus mr omega square sine phi cos phi. So this is the final equation you have now. So in the textbooks you will see that they neglect this term initially and they try to say the justification for why they have not taken this additional term. So currently, since we haven't not dealt with any second order equation reduction, we will consider this term as being neglected. Or in actual scenario, this can be neglected when you are having very high viscous forces and all. So there in the textbook they have derived it completely. We will see how this relates it to the bifurcation what we have studied. That's our motive here. So in that case, when you do that, so you will end up with having only this b phi dot minus mg sine phi plus mr omega square sine phi cos phi. Now if you solve them, you will finally get up as m dot b phi is nothing but mg sine phi times r omega square by g cos phi minus 1. Now if you try to find the fixed point for this, so fixed point is nothing but you find the f of x equal to 0. So in this case you will have two things, either mg sine phi is equal to 0 or r omega square by g cos phi minus 1 equal to 0. So in this case, if you observe the solutions, that means sine 0, pi, all are solution to this kind of system. So that means when you are considering the hoop, the bottom part and this up part both are having some fixed points for the system. And apart from this, if you have one more solution here, so cos phi equal to 1 minus r omega square by g. So that means phi equal to cos inverse of 1 minus r omega square by g. So you have one more solution here. This will happen only when this r omega square by 1 is greater than 1. This condition if it is met only. Else if it is equal to 1, it will become 0 and you will have only stable fixed points like bottom or the top part. So I will just show you how that is. Okay, so we will write that thing down here. So this implies our r omega square by g cos phi minus 1 equal to 0. This is only possible when this value is greater than 1. If cos maximum is 1, so if this value is equal to 1, then this whole thing will go to 0 and you will have only for the given hoop, if you consider in the circular direction, if theta equal to 0, here you consider, so this is actually nothing but 5 equal to 0 pi. So we have drawn the equation like this. So if you remember, this was our phi and this was our rho and r. Now phi equal to 0 means you are at the bottom point. So this was your circle and your bead was. Now when 5 equal to 0, you are at the bottom of the hoop, and when 5 equal to pi represents, you are at the top of the bead loop. So that's how you can interpret the results. Now when you have these two things, you can see that when your value r omega square by g is less than 1, so it's negative when it was, you have the bead and you had two fixed points for it, say at phi equal to 0 and phi equal to pi. Now any point, if it is here, it will try to come to this state and it will try to come to this state. At the same time, any perturbation, if it's given here, it will try to come down in this direction. So that's an unstable fixed point here. Here you have a stable fixed point when r was less than 1. At the same time, when it was r omega square by g is greater than 1, then you can see that your hoop is here, and apart from these two fixed points, you have cos 5 equal to 1 minus r omega square by g value. So this means you have 5 equal to cos inverse of 1 minus r omega square by g. So this is also a solution. So now 5 values, when it is from the vertical, when it has these two values, it can be either plus or minus. Cos negative is also positive, so it can either, both of them it can have. Now based on the r omega square by g value, you can have either any two of these fixed points also. So if you observe this, any fixed point here will try to come down like this. So and anything here will try to, since now this r omega square by g greater than 1, physically this means is that your so physically your r omega square by g greater than 1 implies omega is greater than 1. That means you are rotating the hoop at very high speeds, and at these high speeds you will get two additional fixed points for the system. That's the physical interpretation of this. Now if you try to plot the bifurcation diagram for this, which is what we are interested in, so we see that if it is r omega square by g, and here is the phi values if you are plotting, so you will see that for up to a particular value of say r omega square by g equal to 1, you will see that the system had a stable fixed point at t phi equal to 0. That is, at the bottom point was the stable fixed point. After that, when your r omega square by g is greater than, when your velocity was high, you saw two different stable fixed points being emerging out, and the center being going to unstable state. So say this will not, this is the case where you have minus pi and pi are maximum values or the top regions of the hoop. So you are eventually getting into a pitchfork bifurcation, and you are seeing that you have a stable here, and after the point 1 you are having a branch of stable line. So this is an example of supercritical pitchfork bifurcation. So this, you are able to write it into this form and get to the solution without solving the analytical part. You are able to say that okay, at r equal to 1 I will be getting a bifurcation, and system will be having two different stable states at a given value depending on the conditions that you have. So that's the example for a pitchfork bifurcation which I have planned. So was that clear? Okay. So yeah, so you can take a 5 minutes break. We will then I will then give you one more example of one more bifurcation, and we will go to the flow on circles. Yeah. We will meet at 7:40. Yeah. So yeah. Okay. So now I will show talk about one more bifurcation example, a real practical example to say that okay, these kind of bifurcations are actually in reality happens. So the topic which we will be dealing now is the topic on insect outbreak. So the context is like there is a birdworm called spruce birdworm. So as I have shown here in the right. So these birdworms in the Canada, so they found that these kind of these insects, they when they start growing up, after a particular point, as I have shown in the left figure, you can see that the red regions on the plants or on the trees, so they say a particular name called the tree names are called fir trees. So these trees they target most and they try to eat them up, and due to their, since they pose more of the needle kind of structures there, the red color regions is where the birdworm has actually been attacked. So you can see that the population of the birdworms is very huge, and this usually spreads out. So this kind of spreading they have seen in this kind of in Canadian forests and all. So people were interested in why, how this population grows, or from a simple model can we estimate when the system will outbreak, or when the, at what, after certain how many insects are this system suddenly growing to this kind of high amplitude, of not high amplitude, high amount of birdworm population, how it is growing to. So is there, can we use any, get any models that can replicate this actual dynamics? Was interest in the 90s, and people were working on that. And Ludwig in 1978 he proposed a model which can replicate this birdworm and forest dynamics and all. So his model actually it was able to show the things, and he considered two time scale for the system. So if you observe properly, we can see that the time the birdworm to replicate is very less, and it takes only some 5 to 4 to 5 months for it to replicate faster, which is on a faster time scale when compared to the trees to grow. So the tree takes nearly 7 to 10 years to grow. So compared to that, trees growing is a slow time scale, and the birdworm population expansion is at a fast time scale. So he used this difference in time scales to model the dynamics, and he was pretty able to show the dynamics, how the system will behave, and for which he used the following equations. So we will go through the equation what he has used. So basically he was interested in how to model these insects, how their population, how it is growing, and if you have any predator in the forest, will that, how can you accommodate it and say that when the system, when the insects will increase their population very randomly, or will the population will be dying down if you have more and more predators. So that was the question they were dealing with. And so after this much discussion on the bifurcations which you can experience, so we can see that, so the Ludwig, as I mentioned, he tried to propose a model. Yeah, so he proposed a model wherein he used the population equation. So this is the famous population equation which we discussed in the initial stage, which is nothing but Rn into 1 minus n by k, which where k was the carrying capacity of the population, r is the growth rate, and n is the population of the birdworm, or the population which we considered at the earlier stages. Now additional to this, he added a term p of n, which represents the death rate due to the predation, mostly birds and other insects. So death rate of this birdworm population, he used a term rho of n for that, and he wanted to now see how this predation affects the system. For that he considered a model, and he used a certain equations to model the predation also. How he got the model is like, he observed that when there are very low values of birdworm population, that is like x-axis shown here, when you are having very low values of birdworm, the birds and all, they actually don't see these many birdworms sitting there, and their predation level will be very low. At the same time, after a particular value a, the population of them becomes so high, it becomes sufficiently large that now the birds are able to see their population, and the predation level, that is p of n value, will slowly gradually increase faster than at that point, and it will try to settle down to a particular value called b. So he assumed this form of predation by the birds and other external influences, and he wrote the equation for this in the form, say p of n equal to b n square by a square plus n square. So that was the form he used to model the forest dynamics there. He didn't change any tree species or anything. Instead, he just considered the predation level, and he used the equation of this form, b n square by a square plus n. Now, as a net result, you will see the equation reduced to Rn into 1 minus n by k minus b n square by a square plus n square. Now, our question is like, when will the population be outbreak, or when will you see a high value of insects being present in the forest, which eventually results in that red colored pattern which we saw in the figure. So in order to understand that, what they did was, so say this is equation 1 which we are considering. In this equation 1, first they tried to divide this whole equation by b. So this is the b value. They tried to divide it with b. Equation 1 is divided by, it is divided by b when you do. So we will get n dot by b, which is nothing but Rn by b into minus n by k times n square by a square plus n square. Now once you obtain that, then they put a variable, say x, called x, where n, it is taken as n by a. Now so this implies wherever you have n dot, which means a into x dot, you have a is a constant value, that's why we have put it. So that means here if you substitute this 2 in the, okay, so we will call this as 3. So if you substitute this 3 into 2, if you substitute, so then you will have 1 by b times n dot is nothing but ax dot, it's equal to r by b times n is nothing but ax into 1 minus ax by k minus n is nothing but ax the whole square by a square plus n square. So I am just trying to derive it so that you will know how this one thing, if you are able to collect it, how we are deriving the things. You can do remaining small things for the remaining small examples which I have skipped. You can try to solve them also on this same basis. Then you have r by b ax by k minus, so the a square terms are taken out and you will finally get 1 by x square. Since n by a is x, so this x comes out here. Now this is your equation 4, you see. So now we want to try to non-dimensionalize these equations. This is why we will see why this non-dimensionalization helps us in getting into the normal form, and eventually helps us to tell the dynamics of the system. So to non-dimensionalize the system, what we do is, so here in the first term, if you observe, you have something called a by b x dot. This is nothing but a by b times dx by dt. Now you need to non-dimensionalize such that you will remove this a by b term and you have something in the base as t. So for that you need to convert it into some another variable called tau, and tau should be such that if you take the derivative of it, you should be able to delete this a by b. So we take the inverse of it. B by a times t is the variable if we consider. So if you consider like this, say d tau is nothing but b by a times dt, and if you write it, this is nothing but d tau by dt equal to b by a. So if you try to write it down into, if you substitute this into equation a, equation A if you substitute. So your equation was like A by B dx by dt. This can be written as A by B times dx by dt can be written as dx by d tau times d tau by dt. So this is nothing but A by B times dx by d tau is the new non-dimensionalized term, and d tau by dt is nothing but B by A. So now if you observe, this B and this B you can cancel, this A and this A you can cancel. So in net result, A by B dx by dt has come down to dx by d tau. So say this is your fifth equation. So now you have non-dimensionalized it and you have made it to a parameter of tau. Now I will just explain you one more term here. Say you can consider some small r is nothing but capital R A by B. So that we got it from here. So here you need to remove this R A by B. So for that, if you consider small r equal to R A by B, you would just directly you remove this whole term into a single term small r, and remaining things are all small k. Okay. And in the third term here you have something like A by K. So you consider small k as capital K by A. So this capital K is the carrying capacity. This small k is a non-dimensional variable which we are considering. So if you put these three, equation 6 and equation 7, into the actual equation 4, if you substitute, so we will substitute equation 5, 6 and 7 into equation 4. If you substitute, you will finally end up with the equation dx by d tau is equal to rx into 1 minus x by k minus x square by 1 plus x square. So now this looks in the normal form which we have learned till now. So this is nothing but the population equation and this x square term. Now we can solve this equation in the manner which we have learned previously. So you try to divide it into two different equations, and the point where they intersect is the actual fixed point. Because these two equations you can draw the plots for them. So I will show you first how the plots can be look like, and then I will write it down. So did you get the problem, the insect outbreak question, what it is actually and what we are trying to look into? Yeah, so you can see the screen here, and so now when you, so the blue color represents r equal to r into 1 minus x by k, and we will bring the r value also here. Yeah, so now say when your r value is somewhere here, and I just try to keep the values that are present, and now if you change the r values, you can see the dynamics changing. Okay, so now this red color represents x by 1 plus x square equation, and the blue color represents the r into 1 minus x by k value. Now you can see that when your values of r is greater than 0, you will have one fixed point, that is this point that is intersecting between both the curves. And as you increase your okay, so as you increase your r value, slowly the system this other equations are yeah. So now when I am increasing the R value slowly, okay, here I took the carrying capacity as 1. If I take that value to a higher value, say 9, okay, 9 is too big, so say 4, so I'll have a tangent over there, but I will take 6. Yeah. So in this case, so here you had only one point where the equation was touching. Now when I increase it slowly, you will have a point where you have a tangential curve. So if I zoom it here, you can see there are actually 1, 2 and 3 points that are actually touching there. So here if you zoom it up, you can see this one more fixed point over here. Yeah, so you can see the 3 fixed points being touching over here. So if you change these values, this is how the equation behaves. Now I will just draw them. I don't think the diagram was able to convince more. Yeah, so when we plot this equation, say you had a equation of this form and you have a x1 by x square was looking something like this, and the term one minus r into 1 minus x by k, this looks of this form, and this is the x intercept and this is the y intercept. This equal to 0 if you put, you can get this equation, and say this is x by 1 plus x square. Now if you observe, initially when your r was very less, you will see that there is only one fixed point, and since r into 1 minus x by k is greater than x by 1 plus x square, you will see the fixed point stability being. So from this equation, when this value is greater than x square by 1 plus x square, so it should be positive and it goes towards the right. At the same time, in this region, remaining region, if you observe, x by 1 plus x square is greater than r into 1 minus x by k. So that means it's negative and it will go towards there, and you have a stable fixed point. So now say this is your A point. Now when you increase your r values, you can have 2, 1, 2 or 3 fixed points being standing here. Now if you properly draw there, you will observe that there is a tangent being drawn for here. So you have one fixed point here and one fixed point here. Here this fixed point, we were say that this is a stable fixed point, and if you consider this fixed point, here x by 1 plus x square is greater than r into 1 minus x by k. So that means your whole value is positive and it should be trying to go, sorry, x plus 1 plus x square is greater, so it should be going in the negative direction. So it will try to move out, and at the same time here also x by 1 plus x square is greater than this, x by 1 plus x square is greater than r into 1 minus x, so the whole point is negative and it will try to okay, one second. So this goes like this and this dotted line is like this. Okay, yeah, so this tries to go, and this x by 1 plus x square is greater than the r into 1 minus x, so its net value will be negative, so it will try to go in this direction. Now if it is was a tangent condition, now if you draw it more precisely into, so like this, and say now you have a fixed points like this, so that means you have 1, 2 and 3 fixed points over here. Now if you draw the stability of these 3 fixed points, you will observe that this we were able to observe, and here x by 1 plus x square is greater than r into 1 minus n by x k, so that means it's negative, so it will go in the opposite direction. And here x r into x 1 minus x by k is greater than x by 1 plus x square, so in net result its value will be positive, so it should go in the right. Similarly here if you observe, r into 1 minus x square is going towards the fixed point, and here it is x by 1 plus x square greater than, so it is negative, so it should come in this way. So here you can observe a stable and here stable fixed point. Now if you draw the actual diagram, that is x dot versus x, if you plot, say you have 3 fixed points, say these are the 3 fixed points A, B and C. If you have, you will see that your fixed point region, so 0 is your unstable fixed point, you will observe a curve which is shown here. So this was the curve you can get from this equation that is drawn here. And if you observe the stability, so for this you can just see that this is a stable fixed point and this is a stable fixed point, and so Ludwig called this as the point of refuge and this as the point of outbreak. So the point B is the threshold. So if your insect population value, if it is going above B value, greater than B, then you will be eventually thrown down to the outbreak conditions. Whereas if your values initially starting is less than B, you will see that the system goes to the refugee level, where you will have less population density of bird worms present. So any critical analyst or pest control team, they will try to keep the values of this population near to the A part rather than going to the C part. So C is the outbreak condition point, and the point that distinguishes them both is the B value. So if your population, so you can now clearly mention, if your population is greater than the B value, your system eventually moves on to a outbreak condition and your system stability changes to a very high value, and eventually your the Canadian, as you saw in the figure, the red population, red color dominance starts increasing more and more. So that's the outbreak. So that was the concept that he was interested in, to say when the system goes to a outbreak condition and what is the threshold value which distinguishes these both. So that was the interest of him, and he used the non-dimensionalized method to get to this, into this form of rx into 1 minus x and x square, this general form, to draw the geometric view of it and interpret the results. So that's for what we have used the dimensionless technique, dimensionalizing the thing to a normal form. That was of interest. And if you observe here, the bifurcation that the system has followed here is, initially you had only one fixed point, and then eventually you had one more fixed point and you had 3 fixed points. Now if you look in the backward direction, it is like you had 3 actually, then it became 2, then it became 1. So this kind of bifurcations is what we have learned till now. We have learned 3: saddle node bifurcation, transcritical bifurcation and pitchfork bifurcation. And if you look carefully, you can see that there is a disappearance of fixed points when you are going like this. So disappearance of fixed points you will observe only in a saddle node bifurcation. Not only in saddle node, but when you are having this fixed point was remaining stable, but the other fixed points, they disappeared from the actual stability diagrams. So that corresponds to a saddle node bifurcation. So the system actually, the insect outbreak model which they were able to draw, they found that the system actually follows a saddle node bifurcation method, and they were able to tell which is the threshold they need to consider and when can the system go to an outbreak or a unwanted state. So that was the major study, and they were able to clearly distinguish the bifurcation in that topic. So that's the part in insect outbreak. Are there any questions in this? Okay. So this is the part of bifurcations. So we have seen basic 3 bifurcations: saddle node, transcritical, and pitchfork, and we have seen some practical examples of each of these bifurcations. Now I will start with the topic on flow on circles. So this is very similar to the one dimensional thing which we were learning till now, but some small changes in the, since now till now the only limitation which we had was the system didn't show any periodic oscillations. That is, system didn't start from some point and it didn't come back to the same point. But when you are considering a flow on circle and you have equations for flow on circles, the equations will be of the form theta dot is equal to f of theta, where theta is nothing but the vector field on the circle. It's like a phase of the point. Now if you are having an equation, so till now we were dealing with x dot is equal to f of x form, where your system can either monotonically increase or decrease. This was the only thing the system could exhibit. Now when on a flow on circle, here you can see that the system can start, it can move down and go this way, and it can additionally come back to the same point. So here this time we can see a periodic or oscillations in the system you can replicate using this flow on circle study. So in a basic example, say you have a example of the form theta dot is equal to sine theta. That was the first. So we have studied x dot is equal to sine x equation. Now if you consider theta dot equal to sine theta, so you consider a circle, and for in a general method will be theta equal to 0 you will start taking here, and you will move in the counterclockwise direction, and so opposite will be theta equal to pi condition. Now if you remember, the sine equation was like this. Now from 0 to pi, sine is positive and we drew arrow towards the right. So if it is positive, in flow on circle we will draw an arrow towards in the counterclockwise direction, and from pi to 2 pi the system actually remained in the negative direction. So when you are saying in the negative direction, system will start to move in the clockwise position. So eventually this tells that you have two fixed points, 0 and so sine, the fixed points here is sine theta equal to 0 condition. That means theta equal to 0, pi, 2 pi, all are the fixed points for this. And if you observe, this arrow is going towards this and this is also going towards this. So that means you have a fixed point, stable fixed point over here and an unstable fixed point over here. So that means your theta equal to pi is a stable fixed point. So this is how you try to convert your equation x dot equal f of x ideas into a circular onto a circular map you will be trying to study. And okay, so there is one more important thing to be noted here. So in a circle, flow on circles which we will be discussing, we need to have a unique solution for the equation every time. we have also shown this in the flow on line conditions also, where we say the system meets the uniqueness and existence theorem we discussed there, and we showed that the system actually follows this uniqueness and existence should the system should follow. So in this case, if you had an equation of the form theta dot equal to eta, sorry, theta dot equal to theta, if you had, you will see that theta equal to 0, pi, 2 pi are all the fixed points. But when you consider the velocity, say theta dot value, if you consider, when theta equal to 0, it is 0, but when theta equal to pi, it is pi. And if you come back in the circle, if you come back, start from here 0, you come at pi, and if you come back at 2 pi once again, so when your 2 pi it is there, your theta dot is values is actually 2 pi, not 0. So this tells that you have two different values at the same point. So theta equal to 0 and theta equal to 2 pi are actually the same points, but you have two different values for it. Velocity has two different values, so which is not possible in a actual thing. So we consider that our systems follow this uniqueness and existence theorems, and you will have a single value for at a given point. That is the condition that you need to maintain when you are studying the flow on circles. And yeah, so that is an important thing to be kept in mind when you are dealing with this. Now say you have a oscillator. So these are basically an oscillator. You can study the oscillators using these kind of flow on circle method. So we will start with a simple oscillator or a uniform oscillator. So uniform oscillator is nothing but you have a, say your point starts here, this rotates and come back at a after a time t, and it does it regularly in a periodic way, and it does that, it follows certain time period. Then that kind of oscillators which starts from some point, it takes time t to reach back, and it does it in a uniform way, then it is called a uniform oscillator. Now say the simplest uniform oscillator model which you can write is theta dot equal to omega, where omega is your and frequency of the system. So now, so in a uniform oscillator, omega should be a constant value, so that's why it is rotating after each time. Now if you try to solve it, it is nothing but theta dot is equal to omega t plus some theta naught value. That's simple integration which we can do. So if you do that, you will see that the system solution is periodic. That is because your changes from 0 to 2 pi, theta values changes from by 2 pi, and the time period, so time period is nothing but 2 pi by omega. So what time it takes for you to rotate 2 pi rotation by the frequency, that is how many cycles in a second if you are doing, you will get the time period of the system. This time period remains nearly constant for a given uniform oscillator. Now that's one condition that you can remember. And okay, so in actual scenario, uniform oscillators is not you actually observe. We observe something like a non-uniform oscillator. That is like theta dot equal to omega will be present, but with that you will have some additional terms that reduces the oscillations, or which will eventually damp the oscillations to a steady state. So in order to mimic all this, we add a additional term called minus a sin theta. We will see how this will show the dynamics of the system. So were you able to understand what we are actually trying to do in flow on circles? I think you didn't start this flow on circles. So were you able to understand what is the difference which you are doing in the flow on circle? Okay. So okay, so I will just explain you one example also, so that you can understand what we actually mean in the flow on circles. Okay. So the one of the examples that is mentioned is that, say you have some two people, say you have P and S are two peoples who are running on a circular track, as I shown here. Now say the P is running at an, say this is your center, and he is rotating at a phase of phi from the point S. So P is running at a angular velocity of omega 1, S is rotating at a angular velocity of omega 2. Now we want to know at what time it takes for them, for P to cover S by 2 pi distance. So that means P is rotating, after how much time will the P cover S and move by a distance of 2 pi. So that's what we want to know. And how can you find it using this uniform oscillator model or simple equations? How can you find that is our question. So in order to do that, what we do is, we know that the time period T1 is, say T1 is for P and T2 is for Q. If you say it is nothing but 2 pi omega 1, and for T2 is for S, if you say it is nothing but 2 pi by omega 2, that we just saw. Time period is nothing but, for a uniform oscillator, time period is constant and it is nothing but 2 pi by omega. Now what we want to actually find is the phase difference between the two, theta 1 and theta 2. So the phase difference is nothing but, so since we know that for a uniform oscillator theta dot equal to omega is the condition. Now theta dot is equal to omega we know. So since here phi is equal to phi 1 minus phi 2 is there, if we differentiate it, you will get phi dot is equal to theta 1 dot minus theta 2 dot. And now you know theta 1 dot and theta 2 dot are nothing but omega 1 omega 2, and that is equal to phi dot. Now if you try to substitute this, say we were saying that T is nothing but 2 pi by omega, and now omega is nothing but from this 2 pi by T. So phi naught is nothing but 2 pi by T1 minus 2 pi by T2, and this phi naught is the phase difference between them. So phase difference can also be written in the form of, say 2 pi by T times the lag which you are considering. So this is the time T lag is what we are interested in to find. So this means it is nothing but 2 pi times the T lag that has taken for them to cross, and if you take 2 pi common in that, then you will get 1 by T1 minus 1 by T2. So this implies T of lag is nothing but 1 by T1 minus 1 by T2. So it takes this much time for P to cross S and overtake it by a phase difference of 2 pi. So from this simple model you can tell how much time it will take for the P to overcross the S and cross it by a 2 pi distance. So this is the simple equation. And so in the book they mention the similarity with a two bells that ring in the two bells, and they synchronously they come after some time and they move out after some time. So that's like church bells, when they start with some different frequencies and they eventually come to a single frequency and they eventually go away from them. So this kind of, so it's like a to and fro motion that's going on like this. So this kind of thing can be seen in a uniform oscillator models, and it's pretty explains the scenarios which are ideal in nature, which don't have any other dissipation or anything. But once you have in a real system, you have dissipation terms which needs to be taken into account. So at that time you need to be more concerned of the losses and everything which we need to study. And once we start that, you will see the equations of non-uniform oscillator is what then we should consider. So in order to replicate the actual things, you need to consider the non-uniform oscillators for actual scenarios to be replicated. So the difference here is only that theta dot equal to omega remains same, that is the uniform oscillator. Along with that you will have a damping term which reduces the oscillations to an zero. So this damping term, what it will do is, you have a oscillation, say if it is like this damping term will try to reduce it to a single like this. So this effect is actually seen in real scenario, and we need models to replicate that. And this non-uniform oscillator model, this equation can tell you lot about this, and we will see some practical examples also. Now, so if you draw the equation, so whatever we have written here, theta dot equal to omega minus a sin theta is the equation which you have considered. And if you plot the vector field against theta and theta dot, you will see that theta dot equal to omega was a simple oscillator, and now you have something called a sin theta. So sin theta, you know, it's a curve like this. It is a curve like this which I have shown, which I have drawn here. And omega lifts the, since it is of the form y equal to a plus x. A plus x will may only shift the value from a given point to a higher point. So this a is nothing but the omega which you are seeing here. So that's why your sine is shifted up by omega, and your amplitude of this sine wave is the value a that is with it. So the amplitude represented by the a value, and the distance from the origin shifted is represented by the omega value. So now, based on the changes in omega and a, you can get different dynamics of the system. So okay, I will try to just summarize this what we are trying here, and we will stop with this here. In the next class we will try to analyze this, and here I will show you how the bottleneck problem or the critical slowing down or delay and blowout conditions, how system shows. Here you can explain it more mathematically, and you can geometrically show how the system blows off and all, where you can understand more easily what this all mean. And okay, so I will just mention that, so these kind of equations, the non-uniform oscillator models, they are used in wide variety of systems. They are used in electronics and in biology cases where oscillating neurons and firefly flashings, all these scenarios we use non-uniform oscillators. I will just show you a video. We will discuss on this in brief in the next lecture, but I will show you how a non-uniform oscillator behavior can be seen in real practical systems. So I will just share the screen, and after this we will stop here. So this, in the book, the term is called the fireflies is the topic that I mentioned in the book. So here what we will be seeing is, like, say you have fireflies. So you have different fireflies sitting over there, and each firefly can produce light at a particular frequency. So each individual firefly omega value is fixed. So that is a uniform oscillator, theta dot equal to omega. Now but in real life we see that not the one firefly is influenced by the other firefly. So now you need to take into account the effect of another firefly also. So when you do that, so as you can see here in this figure, in the video you can see that there are randomly the lights are being on and off, and eventually you will see that this random behavior, it goes on synchronization. This is what we have just derived. You will see a synchronization in them, and they will slowly show a same behavior. So they synchronously be on and off, they do very synchronously. So this is a single omega which I have shown. Yeah. So our aim will be like, how can you study this firefly synchronization, or how can you study, say consider a single firefly as an oscillator, then can we say something about inter 2 3 oscillators if they are working together? Can we say something about their dynamics? Can we say when these will become synchronized and they will show a uniform behavior? So all these things can be studied using a non-uniform oscillator, and specifically we use a non-uniform oscillator because the influence from the other firefly is completely different from what the actual firefly is showing. So those influence all we need to consider, and we will discuss in detail about the fireflies and non-uniform oscillators in the next class. So are there any questions till now? Or were you able to understand, or is there any comments or suggestions, anything? Yeah, okay, so we will discuss this fireflies and non-uniform oscillator in the next class, and then we will go to the bifurcations. And I think in the not next class, in the coming week, we will do one tutorial session where I will try to give you the real actual problems, and we will see how bifurcations are seen in them and how you can use MATLAB. I think you have MATLAB before. Yeah, so we can, it's very simple things we will do, and we will try to get how bifurcations are seen in real systems. We will try to model them, and we will try to code it, and we will see how the all the evolution of the systems, how the phase plane is being drawn, these kind of things we will ourselves will develop the code, and we will try to plot them. So that will give you more hands-on things to see how to plot them, and how to, if you are doing a real world problem, you will have a set of equations for your system. Now you can model them with yourself when you are able to do these small things. So we will try to do them. Yeah, so if no more questions, then we will conclude this session here. Okay, yeah, then thank you, have a nice day. Okay.